This video goes into the details of what DNS queries actually look like and their format and their structure, so queries and the resource records that compose them. So recall, a DNS query starts from a client. Say it asks a resolver, what's www.stanford.edu, and this is a recursive query. And then resolver might either answer from its cache or use cache entries, and if it doesn't have a cache entry for any stage of the query, it can ask questions from external servers. So whom would I ask about edu? Whom would I ask about Stanford.edu? Hey, what's www.stanford.edu? And each of these are non-recursive queries, and the resolver then caches those results. So edu, stanford.edu, and www.stanford.edu. So that's a query at a high level. But in the details, the way DNS works is that all DNS information, so in every DNS message, is represented in terms of things called resource records, RRs. And the form of resource record is generally pretty simple. It has a name, so what kind of resource record, sort of the name of the name associated with this record. There can be a time to live and a class. Then there's the type of record, and then the record data. So, for example, a resource record would be named, say, www.stanford.edu. So this is a record for www.stanford.edu. TTL, how long is this record good? Class, so this is the address class. So typically, it's almost always IN1, or it's class 1. So this is for an internet, for the internet. There's the type of the record, and then the data. And so here I'm going to walk through two critical RR types, resource record types. Type A, which is an IPv4 address, and NS, which is a name server. So an A record tells you an address associated with the name. So it'll say type A, the R data is an address, it's the address associated with the name. Whereas a name server record, an NS record, will tell you the address of a name server associated with the name. So a great way to explore DNS and what records look like and what kinds of records you get is to use this cool tool called dig, which I'll use several times. A DNS message, an actual DNS message, its structure looks like this. This is specified in RFC 1035. So at the beginning there's a header which describes the overall sort of what's in the message. There's the question that this message is for. If it's a query, then it's the question of the query. If it's a response, then it's the question it's a response to. And then there are other sections which are empty inquiries, the answer, authority, and additional sections. So it's possible, for example, to send a DNS query with multiple questions in it if you want. Each of these can have multiple entries. So there's a header, then the question, answer, authority, and additional sections are all made up of resource records. So let's look at an example of this. So if I dig www.stanford.edu, this simple use of dig, I'm basically saying I'd like to send a DNS query for the address of www.stanford.edu. And this is what we see come back. So here's the dig output. I'll tell you the version of dig. Here's the header. Some header information, we'll talk a little bit more about that later. So here's the question. I was asking for an address record of www.stanford.edu. So you see here's a record, resource record, even in the question section. And the answer has two records in it. The first is what's called a CNAME record, which I'll talk a little bit more later. But basically it says that www.stanford.edu is actually the canonical name for that. So what CNAME stands for is www-v6.stanford.edu. So there are six different World Wide Web servers for Stanford. Then the address of www-v6, here's the internet, IN, so it's IN1, that's the class, TTL is 1800, this is an A record, and it's for this address. In addition to that, the authority section is telling me who are the authoritative names. These are the NS, the name server records for Stanford.edu. So here are all of these different servers I could ask about addresses in Stanford. The additional section then gives me a whole bunch of just additional stuff. Like here's the address record for Argus. Here's the address record for Erythea. Here's the address record for Atlanta. Here's the Atlante. Here's the address record for Avalon. And so when we think of what DNS is often doing, and the reason why you see this message is so big is that given that it's going to send a response, it tries to send you a whole bunch of extra data, a whole bunch of extra information just to maybe prevent you from asking another query. And so these are A records, these are IPv4 addresses. So quad A records, AAAA, these are IPv6 addresses. And so it turns out Stanford's DNS server is giving me not only the address records of the Stanford name servers, but also not only the A records, but also the IPv6, in case I want to query them over IPv6. So this is what a response to a DNS query looks like. So you can see that there's the header, there's the question section, the answer section, the authority section, and then the additional section. So if you look inside the header, this is specified in RFC 1035. The header is 10 bytes long, 12 bytes long, so it's pretty short. The first 2 bytes are an ID, this so you can pair queries and responses. And then the first 2 bytes is an ID, the second 2 bytes are a bunch of flags. So there's the first that bit I mentioned, whether this is a query or a response. There's an opcode, so standard queries. And there's a return code if there's an error code. Then there's a bunch of flags. So is this an authoritative answer? Is this truncated? All of these sorts of things. So you can see here at the bottom, recursion desired, recursion available. So there are ways where you can in fact ask your resolver for a non-recursive query if you want. Then after these first 4 bytes, there are 4 2-byte values which say how many resource records are there in each section. So how many queries are there, how many answers are there, how many authorities are there, and how many additional records are there. Now then, within each of these of the 4 sections that have resource records, a resource record is pretty simple. It has a name that could be a variable number of bytes long, depending how long it is. Then there's a type, class, and the TTL, with then an RD length field specifying the R data. And so here's the basic DNS name, then the type, then the class, TTL, RD length, R data. And so this is what the sort of on the wire what the byte format of a resource record looks like. Now notice that the beginning of a resource record is a name, but it doesn't say how long the name is. That's because the length of the names is self-describing. It turns out that DNS does a lot of name compression because it's trying to pack everything into 512 bytes. Then names that are repeated through the packet are just, rather than repeated, are just referenced. And so imagine if I'm asking a query about, say, www.stanford.edu, I don't necessarily want to have that repeated many times in the packet. I can just put it once and then refer to it. So the first thing that DNS does is it breaks a name into separate labels related to the steps of the hierarchy. So www.stanford.edu is 3 separate labels: www, Stanford, and edu. Then each label is encoded as a length and then text value. So the length is in binary, so it's basically some number. It's just one byte, and then the text is in ASCII. So for example, if I were to encode 3 www, so W is 0x77, the way this would be encoded in the bits in the packet is 03777777. So this tells me these are 3 bytes, and here they are. Now one trick then that the name compression uses in order to take advantage of the fact that names can be long and repeated several times in a packet is if the length field here in the label is greater than 192, that is, some of the higher order bits are set, then the next 14 bits specify an offset in the packet. And so the way to think of this is that if I see here that the first 2 bits of the length, so 128 plus 64 is 192, are 1, 1, then this length is actually 2 bytes long, this length field, and the later 14 bits specify in offset into the packet. So for example, if I see 0xC0, 0C, this means that the name that this label refers to is at this value minus, take out those first 2 bits, is at offset 12 within the packet. So if I were just to go to offset 12, that's the label that this refers to. So if I have something like Stanford, which is 8 characters long, rather than repeat Stanford many times, it would actually be a 9th because I need the length, right? It would be 0x08, then the bytes of Stanford. I can just say 0xC0, and then the offset of Stanford. It'll be only 2 bytes long. So this is a little bit detailed, but it's important for when I'm going to open up Wireshark and show you what some DNS queries and responses look like. Otherwise, it can be really hard to figure out, wait, what are these resource records and what are these weird values that aren't actually specifying names? So just to give you an idea, so what a DNSA or address record looks like. So this is, say, for market.scs.stanford.edu. So the name region would say market.scs.stanford.edu. This might be compressed, so it might be much shorter. Then the next 2 bytes would say 1, this is an address record. The next 2 bytes would say 1, this is for the internet. The next 4 bytes say 3600, so the TTL of this record, the time to live, is an hour. Then the length of the R data, the length of the internet address, is 4 bytes, and then here are the 4 bytes. And so if you were to see it printed out, say if you're using DIG, you'd see this, but the overall record actually looks like this. In NS record, say the name server record for scs.stanford.edu looks similar, where here we have scs.stanford.edu in the name section. Again, it might be compressed. Then we have 2 saying that this is an NS record. Again, it's the internet, time to live 3600. And then the length is, say, 10. Because it turns out that scs.stanford.edu is compressed because, well, it's been mentioned elsewhere. So really have mission 1, 2, 3, 4, 5, 6, 7, right? And then we have the 1 for the 1 for the length for mission, and then the 2, which is the compressed indication of scs.stanford.edu. So the first 2 bytes in the R data are going to point to scs.stanford.edu. Then we have a byte saying the length of mission is 7, and the 7 mission bytes for a total of 10 bytes. So let's dig for market.scs.stanford.edu. So just use the tool, see what happens. So we're asking, what is the address of market.scs.stanford.edu? So we're asking for an address record. We get the answer. Its address is 171.66.3.10, and here's the time to live of 2050. Authority section. Here are the name servers that can answer this question. Here's a bunch of them: fs.net, mission.scs.stanford.edu, and here's some additional information: address records for these name servers. So that's what this looks like when you ask DIG. We could also ask DIG, what is the NS record for market for scs.stanford.edu? And so we're querying for the NS record, scs.stanford.edu. We see there's a whole bunch of name servers that serve scs.stanford.edu. NS3, NS1, Garage, Market, Mission, and then here's the additional section, which is giving you their IP addresses. Some of them are just IPv4 addresses, some of them are IPv4 and IPv6 addresses. And so here we can see there's so many name servers, and what that means is that if any one of these goes down, I can still go to another one. So even if, say, 3 of these name servers went down, let's say the NS3, Garage, and Market, I could still contact NS1 or Mission to ask questions about names in scs.stanford.edu. So now let's see what those queries look like in Wireshark. So here I've opened up Wireshark and I've set up a filter, UDP port 53, so that's the DNS port, and IP adder, my IP address. This is going to look at DNS requests and responses for my machine. And so if we were to ask this question, dig market.scs.stanford.edu, we get a query and a response. And so here's a standard DNS query, right? Again, Internet Protocol version 4, source, there's my DNS server. And so here's the query. Right? There's a standard query, there's one question, no other records. And so the question is market.scs.stanford.edu. Type A, so I'm asking for an address record, class IN, name market.scs.stanford.edu, type A, host address, class internet. And so here, in fact, we're looking inside the bytes of the packet. Here's all this information about the size, right? We can see here down in these bytes, 00000. Here is, so this is the header of the DNS transaction ID right there, 0x3EAA, flags, questions, etc., 00. Then here's the query itself. So this is the query section. This is market.scs.stanford.edu. If you look down at the bytes, this first byte for market is 06. That's because market is 6 characters long. So we have 06, then MARKET, then SCS, which is 3, so 3 long, 3 SCS, then Stanford, which is 8 long, so here's 8 STANFORD, then 3 long EDU, and then that's the type A, so 01, class IN 01. Great. Now if we look at the response, it's a lot more complicated because remember how many entries there are in a response. So let's look inside this. So it's telling us it's for the transaction ID 03EAA. Standard query response, no error. There was 1 question, 1 answer, 5 authorities, 7 additional. So now let's look at the query section. So the query here, you can see again market.scs.stanford.edu, type A, class IN. And so here's the answer. Market.scs.stanford.edu, blah, blah, blah. Here's the address. But now if you look at this, the name section of this resource record is only 2 bytes long. It's using name compression. So here's that C00C. What it's saying is that C, the first 2 bits are 1, this is a compressed name, and the start of the name is at offset 0C or 12 within the packet. And if you were to count the bytes within the DNS packet, you'd see that market starts at byte 12. So it's saying this name is right there. And so then here's type A, IN, 30, etc., etc. So that you can see, so we're going to take market.scs.stanford.edu, we're going to compress the name entirely. But it turns out you can do some other types of compression. So here is the authoritative, here's an answer for scs.stanford.edu. And so we see again, this name for scs.stanford.edu is compressed. So C0, it's compressed, 13. So this is an address, the one represents 16, so this is at address 19 within the packet, or offset 19. So why 19? Well, if you think, the original market.scs name, which is at offset 12, then there's the length byte for market, and then the 6 market bytes, so a total of 7 bytes. And so offset 19 within the packet is scs.stanford.edu, so you can address not only into the beginning of the series of labels, but any label within there. And so you'll see this happen many times. And so if you start doing digging some requests and open them up in Wireshark, you'll see this kind of name compression. And what this means in practice, right, is that this packet, which had all of this information in it, right, look at all this stuff that's in this packet. All of these different records, address records, name server records, quad address records, fits in 311 bytes. It's a 311 byte DNS response.